So now we are going to see software solutions to the CSP. As part of these software solutions to the CSP, first we are going to discuss about Dekker's algorithm 1. But before going to see this Dekker's algorithm 1, try to recall the three requirements. Three requirements to decide a particular solution is said to be a perfect solution to the CSP. So we need to recall these three requirements first. So the first one is mutual exclusion. So what do you mean by mutual exclusion? So mutual exclusion, it defines that only one process is allowed to enter into critical section at any time. So only one process must be presented in the critical section at any time. This is what your mutual exclusion. But when it comes to the progress, what is the second requirement we have? Progress. So progress, of course, we have given two definitions, but we clearly mentioned that with respect to the numerical, we are going to use one definition that we have already given in our previous sessions, right? But anyway, we are recalling both definitions here. So progress, first definition, if you see, when the critical section is free, if process Pj is trying to enter into the critical section, then process Pi, which is working outside of the critical section, should not block process Pj. Clear? And the second definition for the progress, we have mentioned that when critical section is free, among the multiple number of processes, which process have to be entered into the critical section, that selection of a process should not be postponed indefinitely. So these are the two definitions we have given, but the most usable or else most popular definition for the progress with respect to the numericals based on this process synchronization is when critical section is free, if process Pj is trying to enter into the critical section, then it should not be blocked by other process Pi which is working outside of the critical section. This is the popular definition for the progress, right? Next, we have the third requirement, which is bounded waiting. When critical section is free, okay, so when critical section is free, if process Pj made a request to enter into the critical section, before that request is granted, there should be a bound on number of times to enter into the critical section for another process Pi. What is the definition for the progress? When critical section is what is the definition? What is the definition for the bounded waiting here? So the bounded waiting definition is, it is saying that like this, like when critical section is free, if process Pj made a request to enter into the critical section, before that request is granted, there should be a bound on number of times to enter into the critical section for another process Pi. So this is what the definition for the bounded waiting. Okay, so these are the three definitions we need to recall before starting off this Dekker's algorithm 1, which is part of software solutions to the CSP. So very, very important. We have already previous year get questions based on this Dekker's algorithm 1. So please concentrate on this. If you concentrate here, I am sure you people are going to get very good knowledge or else very good grip on this Dekker's algorithm 1. But one thing I am telling you, people mostly used to feel process synchronization is very difficult. Reason, they don't know how to check mutual exclusion, how to check progress, how to check bounded waiting. But if you concentrate here, I can confidently say that you people are going to have good grip on how to check mutual exclusion, progress and bounded waiting. So we are moving to Dekker's algorithm 1, right? So look at here. So this is what our Dekker's algorithm 1. So this Dekker's algorithm 1 is also called as, okay, so it is also called as strict alternate algorithm. It is also called as strict alteration algorithm. What is that? Strict alteration algorithm. So why it is called strict alteration algorithm? We will let you know. Okay. It is also called as strict alteration algorithm, and it is also called as turn-based algorithm. It is also called as turn-based algorithm. So these are the other names to this particular Dekker's algorithm 1. So it is also called as turn-based algorithm, and it is also called as strict alteration algorithm. So why it is called turn-based algorithm? The reason is, here we are using a global variable called turn. Here we are using a global variable called turn. So int turn. So this is the global variable we are using here. So this global variable turn, property of this turn variable is only one process is allowed to use this turn at a time. Only one process is allowed among the two processes Pi and Pj. Only one process is allowed to use this turn variable at a time. Okay, so only one process is allowed to use this turn variable at a time. So since this turn is the global variable here, this algorithm is also called as turn-based algorithm. Okay, right. So now look at, we are moving to one by one requirement checking. So the first one is mutual exclusion. First one is mutual exclusion. But one thing I should tell you here, we are checking this entire process PA and process PJ in a uniprocessor environment. So in a uniprocessor environment. What is that uniprocessor environment? We are having only one CPU. So since we are having only one CPU, if we allocate that CPU to the PI, okay, or else if we allocate the CPU to the PJ, so that is, so it depends on the priority of the particular process, various criteria. Let's say this PI has higher priority, then we can give this particular PI, we can give this particular PI, or else we can allot the CPU to this PI, and we are allocating this turn variable also to the PI. Clear with me? So we are assuming that PI is having higher priority here. Okay, PI has higher priority here. So that is why this turn variable, first we are allocating to the PI, as well as CPU also we are allocating to the PI. So what is the turn variable now? Initially it is initialized to turn now as a global variable. So since we are allocating this turn variable to the PI, then what is the statement I can write here is, to indicate this turn is allocated to the PI, turn equals to I. So this is what allocation of turn to the process PI. Allocation of turn to the process PI. So once I have allocated this turn to the PI, then we are going to check mutual exclusion. So what do you mean by mutual exclusion? Only one process is allowed to enter into the critical section at any time. Okay, so then look at this, very easy how to check the mutual exclusion. See, to check the mutual exclusion, what you have to do? You should allow one process to enter into the critical section. You should keep one process in the critical section. One more time I am repeating, how to check the mutual exclusion. To check the mutual exclusion, we should keep one process in the critical section. After keeping, or else after allowing one process in the critical section, then take the preemption towards the next process. After allowing one process to present in the critical section, then take the preemption towards the next process and verify the next process status, whether the next process is able to enter into the critical section or not. If the next process also able to enter into the critical section, then it is called violation of mutual exclusion. If the other process is unable to enter into the critical section, then it is called mutual exclusion satisfaction. So what is the scenario here? So how to check the mutual exclusion? So how we are suggesting you to check the mutual exclusion here? First, allow one process to enter into the critical section among Pi and Pj. Any process among the Pi and Pj, let one process enter into the critical section first. So here, since this turn variable is allocated to the I, so first we are executing this turn, this particular process Pi. So look at, so while of turn is not equals to I. So what is the turn? I. I not equals to I. Is the condition true? False. The condition is false. So since the condition is false, then this Pi come out of the critical section, come out of the while loop, correct? So come out of the while loop and it enters into the critical section. And you know that one point we must mention here, this is the entry section. This is the entry section for the critical section, and this is the exit section for the critical section. So this is the entry section and this is the exit section. So as we mentioned that the critical section is restricted area. Both entry and exit both are restricted. So if you want to enter into the critical section, this has to be satisfied. So means that while turn is not equals to I, what is the turn variable? I not equals to I, condition false, right? I not equals to I, condition false. So that Pi is skipping this while loop, Pi skipping the while loop and entering into the critical section. So now Pi is presented in the critical section. Pi is present in the critical section. So after Pi presence in the critical section, okay, after Pi presence in the critical section, take the preemption towards the Pj. Take the preemption towards the Pj. That is what I have mentioned. To check the mutual exclusion, allow one process to present in the critical section. Yes, I have done that. Then I am taking the preemption towards the next process. So now, next process, preemption in the sense we are allocating the CPU to the Pj now. We are allocating the CPU to the Pj. So then, now the CPU is with the Pj. So now process Pj is in execution. So what is the, so here also, this is your entry section to the critical section and this is the exit section to the critical section. So now we are executing the exit section, entry section here. So what is the entry section of the Pj? While of turn not equals to j. But what is the turn variable? What is the turn variable? I, right? So the turn is I now. It is not yet changed. This instruction is not yet executed. So before this instruction is being executed, we have taken the preemption towards the Pj. So now the Pj, for Pj, the turn is I only. It is not j, right? So then while of turn not equals to j, what is the turn? I not equals to j. Is the condition true? Yes. I not equals to j condition is true. So since the condition is true, this Pj is unable to come out of this while loop. It is unable to skip the while loop. Means it is present in the while loop and it is unable to enter into the critical section. So means that among the two processes, only one process is present in the critical section, that is Pi. Are you clear with me? So this is the way you can say that the mutual exclusion have been satisfied by this Dekker's algorithm 1. Among the two processes, only one process is presented in the critical section at any point of time, so that we can say that the mutual exclusion is satisfied. The mutual exclusion is satisfied. Then I hope you are clear with this mutual exclusion checking, right? So what we are mentioned before, what we have mentioned, how to check the mutual exclusion. First, we should allow one process to present in the critical section. That's what I have done. Turn I have allocated to the process Pi and executing the process Pi body entry section, that is while turn equals to I, while turn is not equals to I. What is I value? I, what is the turn variable? I not equals to I. Condition failed, so that this Pi is skipping while loop and entering into critical section. So while this Pi is in critical section, we have taken the preemption towards the Pj and verifying the Pj status, whether it is able to enter or not. So if you look at what is the value of the turn, I only, because it is not yet executed. This instruction is not yet executed, right? So means that the turn value is for Pj also it is I only. So then while of turn not equals to j, what is the turn? I not equals to j, condition is true. So that this Pj is unable to skip this while loop. It is unable to skip the while loop. Getting me? So means at a time among these two processes, only one process is present in the critical section. Hence, we can say that mutual exclusion is satisfied. This is how to check the mutual exclusion in the Dekker's algorithm 1.